Okay, this will be problem 4 of Snell's law. And here it is. We have light is incident upon this piece of crown glass at 45 degrees, which means 45 degrees with respect to the normal, because we always define the rays of light in that way. And then it refracts and refracts again, and on the second refraction, we are looking to see what the angle of refraction is, which is right here. So that's the goal, and this could be a little tedious. There's no really short cut way to just blast through it, so let's look at it in detail, methodically here. I think the first thing I want to do is problem 4, is draw a great big triangle, because really this, well, it's not exactly an equilateral prism, but nevertheless it's going to be, because 60 degrees, 60 degrees, 60 degrees. All right, that's what it is. We have now the light incident at 45 degrees. So I want to draw the normal. There's the normal. And we got the ray coming in, something like this, 45 degrees. We'll call this theta 1. That's 45 degrees. It's the incident angle. It goes into a higher index medium, namely this n is equal to 1.52. We'll keep that in mind. Outside, of course, n is equal to 1 because it's air. And it's going to bend toward the normal. Don't know how much. We'll figure that out. Poof. I'm going to call this theta 2 because we have 2 more angles to deal with. It impacts it here, so I'm going to make another normal and recognize that when we go from a higher to lower index, it goes away from the normal, so it does something like this. There it is, and this is going to be theta 3 here and theta 4. There we go. That part was pretty important, drawing that picture, because everything else will fall into place, hopefully. So what we're going to have to do is use Snell's law to figure out the angle of refraction for the first transition, and that's theta 2. Then we have to make a shift to figure out, when we know that angle, we know this is 60 degrees, what's this angle? So we got to do that. So that's the second problem to deal with. Once we know this angle, then use Snell's law again to equate the indices of refraction and the known angle here to get the last, or the unknown, which is theta 4. So let's go ahead and do that. So we have to really apply Snell's law twice and apply a little geometry once. There, that's not so bad, is it? So we're looking for sine of theta 2. So we're looking for theta 2. So we know that, well, let's just make sure, put up here what the formula is again. N1 sine of theta 1 is equal to N2 sine of theta 2. All right. So I'm, in this case, looking for sine of theta 2. I'm going to write it, actually theta 2, but start with sine of theta 2 is equal to N1 over N2 sine of theta 1. All right. And so that's, and then I'll just go ahead and solve for theta 2. Theta 2 is equal to the inverse sine of N1 over N2. Now, N1 is 1, N2 is 1.52, so 1 over 1.52 sine of 45 degrees. So you plug that into your calculator, 1 over 1.52 sine of 45, quantity, sine to the negative 1 of that, and you get 27.7 degrees. So that is theta 2, 27.7 degrees. Now, that is not the incident angle over here, even if my drawing makes it look that way. So I guess there's different ways to consider this, but I'll go ahead and put my pen against the face of the first interface. Now, the normal is always perpendicular to this face. Okay, so my finger is the perpendicular, but you can visualize that. What we're going to do is we're going to rotate Okay, that's the normal for the first one, and for theta 2 as well. Okay, there's the normal, and there's the angle, 27 degrees. But now our face is shifted 60 degrees. So here it is, and when we start to shift, you'll notice that once we shift, well, 27.7 degrees, now the normal is in line with the ray. In other words, the angle of incidence would be 0 in this case, because the direction the ray is going right now is the same thing as the normal. Grab another pencil here. So anyway, the point is, as we rotate if the face was parallel over here, if this face was parallel to this face like this, then the incident angle over here, theta 3, would be the same value as theta 2. But it's not. So we're going to rotate until the angle is 0, and then we keep rotating more. When we rotate 60 degrees, then from the normal, we have this angle, theta 3. Bottom line is, if we subtract off 60 degrees from that, that gives us negative 32.5 degrees. So that's what we get if we subtract off 60. You don't want to add 60. That you don't want to do. You can go 60 minus this angle. But if we go this angle minus 60, we get minus 32.5. The interpretation of that is, well, when we rotated the face 27.7 degrees, we went to 0, and then we went on the other side. See, it's kind of like on the other side, where normally we have, on an incident and refracted angle, we have the angle on both sides. So the other side means that both angles are on the same side. And at this point, my words are getting too long and drawn out. Anyway, so the minus just means it's going to be on this side, not this side. But the picture shows that anyway. So in other words, theta 3 is equal to 32.5 degrees. And so the final part of this problem is simply to do Snell's law again. This time we're looking for theta 4. So hopefully I'll do this right. It's so easy to mess up the subscripts. So I'm using 1, 2, 3, 4 to keep it all straight. Sine of theta 4 is equal to n3 over n4 sine of theta 3. Just to make sure, n4 sine of theta 4 is n3 sine of theta 3. Yep, that works. All right, whew, good. So, theta 4, the coveted angle we're looking for, is equal to inverse sine of n3. Now, n3 is the same as n2, right? I could have just called this n2, but the subscripts help keep things straight. n3 is inside the material, which is 1.52 and then over 1, because index of refraction. 4 is just 1 again. Sine of 32.5. So when you plug that into your calculator, that should give you 54.3 degrees, and that is the answer we're looking for. Wasn't that a lot of fun? Snell's law applied twice, a little bit of geometry, just enough messing around here to almost guarantee that you're going to make an error somewhere, right? And hopefully that didn't happen to you, and also hopefully this all made sense.